ايه الاخبار يا جماعه؟
كله تمام الحمد لله. ايه الاخبار؟
الحمد لله. انا عايز express my disappointment انه محدش آم، عمل اي حاجه في الهوم ورك او النوت بوكس. حد عنده اي سبب يقوله ليه؟ يعني الريسبونس is zero. هل الدنيا صعبه؟ الناس ما عندهاش وقت يعني؟
ايوه، علشان الجامعة بدأت في مصر وكده، فالدراسة بدأت في وقت قليل بس.
يعني الموضوع اعتقد يعني المفروض ما ياخدش اكتر من مثلا، يعني to be fair يعني خلينا نقول ساعة maximum. ف يعني the whole point of this إنه يعني النهاردة is session number 8. The original plan was to do this for 10 sessions. um, بعد كده يعني the course is gonna stop if you don't really apply the things we're learning together. It will be like you never even came to this course. Um, and this will be يعني this will actually bother me a lot. إنه I spend all this time trying to make this a good learning experience, and then people just come and listen to the lecture for an hour and a half every week. And then 2 months down the road, when this is all over, you don't even know, anything that we talked about. So the only way for this to really stick and make sense on the long run is to actually somehow apply it. And I'm trying to make this very easy for you. Like you have the code, it's already running. When I ask you to go and change one or two things or try to answer a couple of questions, it's just for you to think about the stuff we've talked about and maybe build some intuition yourself. Um, and I mean, we're only really just doing the basics of the basics, nothing fancy, nothing complicated, and we're going at a much slower pace than what I originally intended. Um, فيعني hopefully things are easy to follow and easy to apply. But if you just do nothing and come to the class every week, I don't think you're gonna learn something long term.
اسمح لي أتكلم دكتور.
اتفضل.
معتز حرز الله من الأردن بداية.
اهلا وسهلا.
أهلا بك. بداية شكرا جزيلا لحضرتك وللجامعة اللي رتبت الكورس، وحقيقة شيء فعلا رائع، enlightening للجميع. معك حق تكون disappointed. There are no excuses. في justifications no matter what we say, but there are no excuses. We should have spent more time for this and give it more priority. بس يعني واحدة أو جزء من ال justifications were having three courses running at the same time, being مش illiterate بس يعني شوية struggling with the technology, having to install virtual machines on my laptop, trying to install Python from zero, trying to run the code. هاي كلياتها شوية يعني كان في شوية excuses ممكن تكون يعني هي سبب. بس I agree with you إنه we should have put some more time into this لحتى إنه حتى نستفيد منه. أنا بس حبيت أعتذر عن التقصير وأشكرك على على الجهود الرائعة اللي حضرتك بتقدمها. معجب جدا بالكورس وبالجهود اللي عم تعملوها. واعذرنا، انا بعتذر، اسف، وان شاء الله انه نحاول انه نرجع نشوف الريكوردينجز ونشوف ال الكود اللي حضرتك قدمت لنا اياه. حقيقة شغلة ديتيلد مش موجودة بكورسات تانية. أنا at the same time عم باخد artificial intelligence as a practitioner في Amazon Web Services، وعم باخذ كلاود انجينير برضه في الامازون، حتى اكون جديد على هذا الموضوع. عم بحاول تو كاتش اب وذ اي اي ريلم اللي عم بيتكون بالعالم حاليا. بس يعني اتس اوفرويلمينج، وفي كتير شغلات جديدة، فالليرنينج ريسبونس شوية بطيء. بس أنا حبيت أحكي الكلمتين هدول لأنه ببالي والله من البداية. شكرا لحضرتك، شكرا جزيلا، ولجامعة النيل. ونعتذر عن التقصير، وإن شاء الله نحاول إنه نتدارك الموضوع المحاضرات الأخيرة إن شاء الله. وشكرا لك.
جزاكم الله خير يا معتز. يعني طبعا one of the things I'm looking forward to hearing is always feedback. يعني يعني أنا دايما بسأل if people don't do this because things don't make sense or there is anything blocking people from actually understanding or running the code or things are just overwhelming, then it's my fault. It should be something that I changed so that this becomes a good experience, a good learning experience for people. Again, at the end of the day, this is stuff I have already learned, alhamdulillah. My intention is for you to learn. Like if I push you one way or the other, it is because I would really like you to benefit from this course. Uh, and everyone here is coming from a different background and will think about how to use this course in a different way. Some people are already way ahead in their professional journey, and this for them is like just, dipping their toes in a new field, in a new era, and thinking about how do I implement this in my already ongoing work. And some others here are students trying to decide which direction do I want to go after graduation, or maybe they have already graduated, but they're trying to learn something to prepare themselves from job market or whatever. And I'm perfectly happy and fine to support anyone no matter where they are on their journey. And that's why maybe I'm a little bit pushy here, because also I've gone through this myself. I've gone through the phases in my learning journey where I would just be listening to videos and going through them because I would really like to finish a course, for example. But then I find 2 months later that nothing in that course is actually sticking, and I'm having a hard time recalling the stuff that was discussed in the course because I didn't take my time and try and internalize the concepts, get my hands dirty and run some code, face some, errors and think about where they're coming from, do my own experiments with the code. One of the good things about, a computational space is experiments are cheap. Like if there's something that, you're trying to understand, what if I change one thing or the other thing? What if I structure my data this way or that way? You can empirically do this. All it takes is for you to make the change in the code and run it and wait for the result and then think about the output and how it compares between different conditions. And in practice, this is what we do, in a lot of times. I maybe mentioned this many times now that there is a lot of empirical learning that happens in the space of deep learning. Because even though we can theorize about a lot of things, when we apply things practically or empirically when we're training models and stuff, we're always surprised that some results don't really align very well with our conceptual or theoretical understanding of how things are supposed to go. And this in and of itself actually is a skill if you would like to, have some experience in learning. Like you have to think about what experiment do I do in order to test one hypothesis? Like, how do I do this in an efficient way? How do I get my answer to what parameter is best to use for my model? And you don't want to waste too much time because you would like to arrive at like the best, quote unquote, the best possible model or parameters that you would like to use for your own model that is fitting your objective and fitting your data and blah, blah, blah. So that the testing and trying to think about how do I troubleshoot why my model is not learning, for example, is a skill in and of itself. And it's not a very teachable skill, if you will. Like I can show you ways, I can show you how I do things, but everyone is going to have their own perspective on how to do this. Okay. I apologize for ranting, but I really wanted just to maybe motivate people a little bit more to before this is over, because we're gonna part ways. Maybe we can, I don't know, if you're interested, we can reconvene in a few months and do a little bit more advanced concepts that people now have the basics. Um, I'm pretty sure, like, I had hoped that we go faster a little bit in terms of covering concepts, but I have no problems with slowing down because if we get the concepts right, anything that builds upon the concepts are going to be easy for you to follow, even without me, sitting there and talking for an hour and a half. Alhamdulillah, we've covered the all the math behind like the neural networks. Hopefully, you have a very good understanding of the math that happens at every single step. We cover as many possible parameters that go into the actual architectures of the networks themselves. Um, we've been talking about the overfitting and underfitting, which is a very practical problem when it comes to training models. We talk about today, last time we talked about dropouts. Today we're going to continue talking about the regularizations. Um, I've shown you a few ways on how you could, in PyTorch, build your network. So we talked about initially when we started building networks in PyTorch, we talked about the easy, class of the neural networks and use the sequential model to build um, our networks. And last time we introduced the idea of using classes and using the object-oriented programming in building more sophisticated classes. Again, we're showing this with very simple examples, but as you know, if you have a good understanding of this, this scales up really, really well. It doesn't matter if you would like to have, three hidden layers or 20 hidden layers. The idea is exactly the same. The scaffold of the code is exactly the same. You really just need to change a few, lines here and there, and you have the foundation for doing this. And in the remaining two sessions that we have together, I'm hoping to also give you a little bit of some ideas about the optimizers because this is, I think, one of the important things. And then maybe we talk about the model evaluation in a more formal way. Like we have been just doing like regular visualizations of how the training accuracy is, how the testing accuracy is, and just calling it a day and understanding how the models learn. But we can have more formal discussion about like proper model evaluation as you train multiple models or more larger scales models. Um, and when we arrive at this point, you would have learned everything in terms of like the basics of how do neural networks work. And when you go and learn one architecture or the other by yourself, besides the intricacies within that architecture and like why the architecture came about and what problem it's trying to solve, it's basically going to be like having some Lego and putting the blocks together to arrive at a different shape. Um, all of the blocks have been covered in the basics that we talked about. There is going to be, everything that will be within a certain architecture will probably be something that you have seen one way or the other. The differences are going to come from how do you put these Lego pieces together to arrive at the final architecture. And you will see that when you put things a certain way or the other, that the output is going to be different. And this is what makes the different architectures in the networks. All right. Um, Let me share my screen. Okay. All right. So last time we were talking about the the regularizations, and we spent some time, actually most of last session, talking about the dropouts. Um, I started talking by saying that we can, by and large, classify regularizations into three levels of regularizations. One is like on the level of nodes, which is the dropout. And, just to quickly recap this, the idea here is we would like the network to not rely on a single or a set of nodes um, when it's learning. So if the network is capturing a lot of information in a single node, this is not a behavior we would like to have, because then the weights of this node, the output of the network is going to be very sensitive to the change of a certain input because of the emphasis of the weights associated with this node. So the idea is we randomly, with every mini batch, drop out a set of nodes, and then we do this during the training. The hope is to distribute the learning across all the nodes because of the stochastic behavior of turning on and off nodes. And then we also emphasize the concept that this is only something we do in training, but once we shift to evaluating the model or actually using the model to predict something and to produce the output, we use the full network, because hopefully now that we've done this dropout process, the weights that the model has learned for every node is now a good representation that can be used. I've seen a hand come up and go down. Is there a question? Okay, I'm gonna go on. So the other or the second kind of regularization is at the level of loss or the cost function. So the idea here is for the cost function regularization is um, the goal of learning or the goal of the model, or how we evaluate whether the model learned well or not, is we predict something, which is the output of the model, and then compare this to the ground truth, which could be, depending on the problem, if it's a regression problem, then we compare the actual values to the original values. If it's a classification problem, we compare the classes we predict to the labels, the input labels, which is the ground truth. And then through the difference between the predicted value and the ground truth values, we know how well or bad the model is doing. The idea of loss regularization is we would like, as the model is learning, to basically make the predicted output as close as possible to the ground truth. We would like to have some constraints on the values of these weights, meaning that as the model is like giving me a very accurate predicted output, um, it cannot do this while having weight values that are very large. And this is now a place where I can ask you, given everything you've learned, why is it bad to have, I'm talking about the absolute values of the weight, right? So we learn the weights, the values of the weights and biases in the network. And what I'm saying now is we would like the network as it's training to not have very large absolute values of the weights. And my question to you is, why do you think this is the case? What's the harm in having, or why should we even care about having large or small weight values?
Overfitting, perhaps?
Yes, so overfitting is exactly what we're trying to get away from. But why? Like, if I have two networks that have the same performance when it comes to loss, but one of them has large absolute values of some of the weights and the other doesn't. Why am I trying to tell you that the network that has some high values of weights, a worse network basically than the other one?
Because it will capture some of the features more biased in a more biased way than others, than if the weights are more balanced.
Yes, it's I would say a version of this. The idea is you are really amplifying the importance of certain features, right? So if you think about the math, the what where does the value of the weight, like the absolute value of the weight, come into play? It comes into play when you multiply the input value. This input value could be the actual raw input or the output of the previous layer, right? Depending on where the weight is or which node it's connecting, which two nodes it's connecting. Um, Whatever the input you have gets multiplied by the weight. So if this weight is a number like 2, it's gonna um, change the data in a different way than if it's 200, right? And the way I think about this is weights could be thought of as like amplifying nodes or sorry, amplifying knobs. So if you have some set of inputs and one of your knobs is turned all the way to the right, it means that the network becomes very, very sensitive to a certain input, right? Because once you multiply the input by that weight, it affects the output way too much, which exactly is the overfitting that we're trying to get rid of. So, in other words, when we have very high values for the weights, the network is very, very sensitive to very small changes because even the tiniest of the changes becomes amplified way too much, which means that the network is going to learn more of the noise because it's trying to minimize, right? It's trying to minimize the difference between the predicted value and the ground truth. So in order for it to achieve this, it has to arrive at certain values of the weights where the where the predicted value is very close to the output of the value. So because now the weights are very large numbers, it's basically going to have these weights set to something that learns the noise of the data. Because if the weights are a little bit off, this small difference is going to be amplified way too much. And then the loss is going to degrade. The loss is going to be really bad. So then, in essence, the network will have to learn the noise and will have to learn the individual data points of the training set. And when we go and generalize to a different data set, the performance is not going to be good. Hopefully that makes sense. So we have two forms of regularization. So the general concept before talking about them is what you see here. We have the cost function, which is what you see here. The cost function is a function of our parameters, which are the weights and the biases, right? This is what we've been doing um, throughout the course so far, that we just calculate the loss function. The loss function is a function of the weights and the biases. And we talked about how this is done and what kind of cost functions are, used in different cases and whatnot. The idea now here is we are gonna put some form of something we call the regularization term, and then have this multiplied by some parameter that would control how much of this regularization I apply. And this is my second question to you. What do you think? What do you think a high lambda value here would result in? Okay, let me repeat my question again. I'm saying now if we regularize the cost, we add some term which does the regularization, but we're basically using another term which is lambda to scale this term. So my question to you is, do we want this term to be large or small, and why?
Perhaps a small to avoid saturation.
I agree with the first part. We want it to be small. What do you mean by saturation?
I mean, if it's too huge, then we lose the linear part of the cost function.
So we want it to be small because at the end of the day, what are we trying to optimize the model to do? We are trying to optimize the model to minimize the difference between the prediction and the ground truth, right? So we still would like this term of the cost to be the predominant term. If we increase the regularization term too much, this entire cost function will become basically um, kind of a restriction on the values of the weights, regardless of the difference between the predicted value and the ground truth, right? So if, for example, this loss function, if this loss term or this cost function here, let's say if this loss is 2, and this regularization term is also 2, and I multiply this by 10, this means that this term on the right-hand side becomes 20, and this is 2. So if the model is trying to learn some parameters to minimize the overall cost that is happening because of the actual loss function plus the regularization term, the model is going to prioritize optimizing the regularization a lot more than optimizing the actual loss function. And we don't want this to happen. We would like the model at the end of the day to still prioritize learning the weights that result in the minimum distance between the predicted value and the ground truth. So that's why we set this tuning parameter, lambda parameter, to a very small term. So in other words, think about it this way. I would like the model to still learn this term here, but in doing so, I will penalize the model if it learns some very huge weight values. Okay? All right. So what are these regularization terms? Like we've still been saying regularization, and there's two very common types of penalties or regularizations. And these come from, if you've done any statistics course, these are very popular methods used in regular statistics. One of them is called the L2 regularization. If you've heard the term Euclidean distance before, this is the foundation of it. And the L2 regularization, basically, what it does here is it takes the weights across the entire network and it squares each one of these values and then sums all these weights into a single vector. So this is what the notation here means. We are summing from I equals 1 to I equals n. This n here is the number of weights, which is the number of nodes. And for every weight value I, we're squaring this, and then we're taking the sum of these. And if you think mathematically about this, this term here, because we're squaring the weights, this is going to very heavily penalize the large values or the outlier values of these weights. If you have a weight value that is really, really high, when you square it, it's going to grow quadratically. And when this happens, the cost function is going to go way too much. So as the model is doing back propagation, it's going to realize that this weight is actually causing way too much loss. So I need to bring this down. So the result of adding this is also another term of it, is actually called the weight decay, or the ridge regularization, which is very commonly used in the statistics space. What I was saying, yeah. So the result of this is you very heavily penalize the outlier weights, and you try to bring them back towards the zero. And because, again, of this quadratic relationship, the L2 regularization does not really bring any of the weights to an absolute zero. Because of the nature of the quadratic relationship, if you take your time and draw like a quadratic function, you will see that in the far end of the range, like as you increase the values on the x-axis, a very small change is actually going to make a huge difference in the y-axis because of the squaring function. But then as you get closer to zero, you're going to get into the diminishing return space. You change the, if you change the value, the x value from, let's say, zero point 0.2 to zero point 0.1, the change is going to be very different when you change it from 3.3 to 2.9, for example. Even though the change or the delta on the x is zero point 0.1 in both cases, the zero point 0.1 when you square it, like when you square 3 versus 2.9, is different from when you square zero point 0.2 versus zero point 0.1. And if you go and mathematically test this, you will find that with the smaller values, the delta becomes much, much smaller. And that's why, as the model is trying to optimize this, it will reach a space when all the weights get closer to zero that it doesn't really make much sense to modify them further. So it doesn't really cause any of the weights to be an absolute zero, because before it gets to zero, the model hits this space of diminishing returns that as I decrease the values of these weights more, I'm not really minimizing the cost that much because the delta is way, way smaller as I get closer to zero. Does that make sense? Okay. All right. So we talked about this already. That we would like the purpose of the L2 regularization is that we would like to keep the model weights small, and we explicitly said, like, discussed the idea of smaller weights equals simpler models and larger weights equal complex models, because again, when you have larger weight values, the network is very, very sensitive to small changes in the input. And hopefully now that makes an intuitive sense to you. And then we also talked about why L2 does not really have any, or does not really lead to the weights being set to exactly zero, because as we approach zero again, we hit this diminishing returns phenomenon. And then as the model is optimizing, it doesn't really make sense to keep pushing the weights down. The other kind of regularization is called the L1 regularization or the lasso regularization. And this has a very different working paradigm here and results in a very different output as you're optimizing the weights. The idea still remains the same. We would like very much to find the weights and the biases that minimize the difference between the predicted values of the network and the ground truth. Um, in doing so, when we apply the L1 regularization, we don't really penalize the outlier models. The outlier weights. The L1 here takes the sum of the absolute values of the weights. Meaning that instead of squaring weights and adding them, we just take the absolute value of the square so that the positive and negative don't cancel out each other. And then we add this, and this becomes the regularization term, which is then multiplied by the lambda and then added to the cost. So what effect does L1 regularization have on the data? Basically, because unlike the L2, which is a quadratic function, meaning it's the square of the weights, here we're taking the absolute value of the weights, meaning that this is really just a linear function, right? So because this is a linear function, it doesn't matter where you change x along the x-axis, the change in the y is always going to be the same, right? So if the same example that I give you, if a certain weight is 3 and I reduce this from 3 to 2.5, this is going to produce exactly the same effect as taking the weights from 0.5 and reducing this to 0. So as the model is optimizing, it's gonna keep like as it's reducing these weights, it will observe consistent gains on reducing the weights until it hits zero, and then a certain weight hits zero, then it will see that this term goes away completely. So in the quadratic, we said this doesn't happen because as the model is trying to reduce the weights with every epoch or iteration, there is going to be diminishing return. So it will be reducing the weight down and not really seeing much change in terms of the cost. But with the L1 regularization, because the same reduction in the value of the weight, the absolute value of the weight, is going to lead to the same consistent reduction in the cost. So the model, as it's optimizing, it will keep reducing the weight until it hits zero, and then this becomes the absolute maximum reduction it leads to. And then what does this practically mean? Practically, this means that when using the L1, you're basically gonna end up with a set of weights that are gonna be exactly zero, which, in machine learning lingo or in statistics even, we're going to call this a sparse weights vector or a sparse weights matrix. The word sparse comes from having way too many zeros. So if you had originally, let's say, I don't know, 64 weights, or this is a very small number, but whatever. If you apply L1 regularization and you find that there is maybe now 48 out of the 64 are actually zeros, it means that the network is really just learning 12 weights, and the rest of them are basically to the network are irrelevant. Um, do you think this is a good or a bad thing? Because there's a lot of things to think about in this space. I mean, there's already a few things that I spoiled here. Maybe I shouldn't have showed you the text, but let's pretend it's not here and have a discussion. Any takers? No? No one? Okay, let's try and simplify it maybe a little bit more. Um, has anyone here done any classic machine learning before? Okay, what about, let's say, anyone here has done any bioinformatics? Let's say something like, have you processed single cell RNA sequencing, for example? Okay, so the L1 regularization, the behavior of the L1 regularization leading to the sparsity means that essentially, as the network is learning, it's performing something called feature selection for you. So in classic machine learning problems, typically when you're approaching a problem, there is something called feature engineering that people go through, meaning that you go through your data. If you have a data set where you're trying to learn some predictors for a property or some predictors for a certain behavior, like for instance, you have some patients, the patients have some clinical data associated with them, meaning what's the age of the patient, what's the medical history of the patient, has this patient taken any medication before, has this patient been hospitalized before? And the outcome is, let's say, the probability of this patient getting a certain disease. So in a classic machine learning problem, what you do is you examine the feature space, meaning you go through all these features, you try and understand, are there any correlations between these features? And then you ask some questions of, are any of these features are relevant to the predictive power of my machine learning model, for example? So you go through a process where you actually engineer some of these features. You do some analysis on these features. You find some correlation. You find some um, um, what is it called? Relevance to some of these features. And then you decide that, you know what, when I build my machine learning model, I am only going to consider the factors of previous medications and age and whatever. And this is a deliberate process that you do before training a machine learning model. In this, yeah, so collinearity is exactly like saying that two features are correlated. That's exactly it. So in applying the the L1 regularization to your weights, you're essentially making the network do this for you. The network, as it goes through the features, it's gonna set, as it goes through the training, it's gonna set some weights to zero because of this L1 regularization that you chose to apply. And when you do this, obviously, when a weight is set to zero, then any input feature that is multiplied by zero is going to be zero, and this is going to propagate to the entire network. So essentially, what you're doing is you're basically setting this feature to zero. So instead of starting from, let's say, 100 features, because you have a sparse weights matrix, you've multiplied maybe 90 or 80 of these 100 features by zero. So really, the model is predicting what it's like or producing its output only using 20 of the 100 features. And you can go back and check which of the features, depending on the weights, which of the features are being used to make these predictions. And you can learn a lot about your data that, you know what, these features are really not important because the network can really learn without having seen any of these features because they're essentially set to zero. It did see them as numbers, but then it multiplied everything by zero, so it doesn't really learn anything from them. Okay? One
دكتور
problem.
بس هو حكاية sparsity دي عاملة شوية زي dimensional reduction ولا لأ؟
So it's very different. So when you reduce dimensions of something, you don't really set them to zero. When you reduce dimensions, it's like you take the features and you compress them into, let's call them meta features. Like for example, if you have, think about PCA, for example. Um, PCA, when you apply PCA to a data set that has 100 features, how many PCs do you get? How many principal components do you get? Have you used PCA before?
Yes, I have used it before بس مش فاكرة صراحة يعني
طيب
معرفش يمكن 50.
لا, you get the same number of PCs as the number of features. طيب هو why do we even do PCA if we get the same number of PCs, principal components, as exactly the same number of features? Oh, in your case, you're saying we get 50, we get 50 because you were setting whatever you were doing after PCA to only use 50 components. So why do you care about using 50 components or 30 or 10?
هو بحيث أركز بس على important features بالنسبة لي فأنا بتكلم على أساس كده.
طيب what does the PCA do in order to tell you focus on important features? Does the PCA tell you which features are important?
لأ بس يعني هي في الآخر بتطلع زي direction أو حاجة كده تقريبا مش فاكرة قوي بس هي
Okay.
بتطلع الدايركشن اللي هو المفروض أروح فيه اللي هو الاتجاه المفروض أمشي فيه من الآخر عشان أجيب أحسن features أو أشتغل على أكتر حاجة هتفيدني في الداتا
Okay.
يعني.
طيب هو the PCA actually tells you the bigger sources of variations. So for example, it captures the variation, um, it captures the axes of variation because you mentioned directions. It captures the axes of variation in the data set, and it assigns something called PC loadings, which tells you which which of these features are actually responsible for some of these axes of variation. And this is something that goes in a descending way as you progress through the PCs, which means that, for example, your first principal component is the component that captures the maximum variation of the data. And mathematically, what it does before, without getting into too much details, Mathematically, what happens is you're projecting all these features into a space where all these principal components are orthogonal to one another, meaning the axes are perpendicular to one another. And as you do this process, you kind of take the features and realign them into a separate space so that they're on the same axis. And then this is how you capture more difference, for example, in PC1 versus PC2, because the way you spread the features along this axis lets you see how these features spread on along this axis. You can go and check like the math behind PCA. I think in channels like StatQuest, there's a very detailed explanation of how this is done. There's also the Serrano Academy channel. He has a very good explanation of PCA and eigenvectors and eigenvalues and whatnot if you're interested. But the bottom line, just getting back to what we were saying, to answer your question, the PCs doesn't feature select. The PCs doesn't set anything to zero. The PCs tells you the variation in the data is the most variation of the data comes from certain principal components, and these principal components have some loadings or some features which contribute more to the variation. So when you would like to reduce the dimensionality, you use the principal components as a proxy to where the variation in the data is coming from. This is different from the L1 regularization because you're literally setting the certain features to be zero, as if they never existed. So if you take the trained network and you examine which weights are being set to zero, and you remove the corresponding inputs completely from this data, and you run this through a network, you should be predicting the same thing because the features that were there are just noise. They're not being used in the predictive power of this network. Does that make sense to you?
Yeah, okay. Thank you.
Okay. So one very drawback, one very significant drawback of the L1 regularization is when it comes to highly correlated features. So if you have some collinearity in your data, let's talk about gene space because this is a very good example to this. Usually, when you do something like an RNA sequencing experiment, you get way too many gene expression values. Like, let's say after filtration and blah, 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 you get like 15 to 16,000 genes, for example. I would strongly argue that, and anyone probably in the field can agree with this, that these genes, a lot of them are co-expressed. Like some of these genes are downstream of a certain transcription factor in the cell, and once a transcription factor gets fired up, then there is like an entire network of genes that are co-expressed together or co-inhibited together, right? So when you go and let's say put these input values into a network, not every value of these genes are important. Like if you're trying to understand the behavior of a certain cell and why the transcription changes, let's say as a response to a drug treatment or like I don't know, disease or whatever, not every feature there is important. But so the way the L1 regularization handles this basically, as soon as it identifies that certain features are correlated with one another, is it basically picks at random one of these features to be representative in the network, and then it zeroes out all the other ones. And this, from the perspective of having some prediction, is okay, but in the perspective of these features having different meanings could be problematic. Does that make sense?
Why do we take it randomly?
This is basically how the regularization work. We don't do it ourselves. The regularization, because of how it minimizes the cost, when you have in your data a set of highly correlated features, as the network trains, and then if you examine the output, you will see that among these highly correlated features, one feature stayed, like the weights for this feature stayed as a non-zero, and the rest of them basically were zeroed out. Because as the network is trying to minimize or penalize the values of the weights without harming its predictive power, right? Because all these features, like remember, as the network is training, it's trying to minimize the whole term here. And we said that because this is just an absolute value of the weights, in order for the model to effectively minimize these weights, it's going to keep reducing the weights until they hit zero. So the model is trying to maintain this predictive power while keeping this term at minimum. So if there are 10 features that really do the same thing to the cost, but having every one of those weights as non-zero is increasing that cost. So the model is not really benefiting anything when it comes to the predictive power, but it's adding to the final cost. So it's in the model's best interest to keep only one of these features because they're all doing the same thing when it comes to the prediction. But because every one of these terms being non-zero is going to increase the cost, it's in the model's best interest to only keep one of these weights and set the rest of them, the 9 other ones, to being zero. So the outcome of the behavior, when you have a set of correlated features, because they all have the same predictive power, the when you apply the L1 regularization, the model keeps a single one of them and then removes the others. Which one? It's just a random process, depending on, like, you could run the network 10 times and every time it just zeroes out everything and keeps a single feature, and every time it's a different feature. So when you then go and try and look at the weights and look at the features and try to learn about the features of your data and which ones were important, this becomes misleading. That's the point that I'm trying to make here. Does that make sense to you? Why we end up with, when we have highly correlated features, we end up with a single one that is only represented in the network and the rest is zeros? Okay. All right. So hopefully you have a good understanding now of why we use regularization in terms of, the loss regularization. Remember, don't get confused. The term regularization also applies to dropouts. This is the general term that we use to regularize, but in that case, we're specifically talking about the loss regularization. So hopefully the L1 and L2 make sense to you. All right, so let's quickly talk about how we implement this in code. And basically, the bottom line is the L2 is really well integrated in the PyTorch code, and all it takes to do is once you when you define your optimizer, all you need to do is to use this additional argument here. So remember previously in any network that we trained previously, when we set our optimizer, which is the stochastic gradient descent, we would just pass in the parameters of the network and then set some learning rate, and that's it. This is now a new term, which tells you, let's set the weight decay, which is the L2 regularization, to a certain value. And this value here, the L2 lambda, is basically what? This lambda value here. So by default, if you don't really define anything here, this doesn't get applied. Once you define it, you don't really define anything in the equation except for the lambda value, because then the rest of the equation is a function of the weights that the model is learning. Okay? So this is basically as far as, applying L2 regularization go, and then the rest of the code is going to be exactly the same as we've seen before. That's the only thing that you need to do. So you take your optimizer and you add a weight decay term to it, or argument to it. Then the training here is exactly the same. I believe this is from last time's, what was it? Was it the iris data?
Yes, it's the
Yeah.
iris.
Yeah. So that's basically the exact same code. Like, you can go through it. I'm not really doing anything. You've seen this hopefully many, many times now. We define the number of epochs. We define a function to train the model. These are empty lists to store the accuracies and the losses. Within every epoch, we loop through this. We get our X and Y from the training data loader. We compute the Y hat, we compute the loss, then we do a back propagation. We start by setting gradients to 0, then we do a back propagation, then we update our weights using the optimizer.step. This is just us recording or updating the accuracy and loss lists that we initiated, and the training losses. And then, yeah, this is what we talked about last time. We set the network into the evaluation mode before predicting the labels. And we talked about this extensively last time, that regularization does not really happen in the testing, it only happens in the training. And eventually, last time I showed you that I set it at the top of the training loop. Here, I'm setting this at the bottom of the training loop. We said last time it doesn't make a difference, so I'm showing you one of each. As long as you set it anywhere after the evaluation, it doesn't really matter. And we plot the results. So what you're seeing here, this is what I told you last time, is we're not really going to see much difference with and without the regularization because we're training a very simple model. But you can try a few things if you'd like to observe some differences. You can actually, you see that the training, the loss is not getting down by much because I have reduced the learning rate a little bit here. I set this to 0.001. I think previously it was 0.005 or something. You can reduce it even further and see that as you keep going with more epochs, the learning becomes slower because the learning rate is smaller. Hopefully you know why. But basically, reducing the learning rate is gonna artificially make this model worse so that you see some benefit or difference when it comes to regularization. There is then this code is basically showing you I'm doing exactly the same thing, but now I'm showing you the effect of varying the weight of regularization. So I'm using a range of lambda values here, basically between 0 to 0.1 in 10 equal intervals. And then I'm looping through the same functions and every time just using one of the lambda values. So you're going to essentially train 10 models, every model with a different lambda value. And this is basically what it looks like. So these are the curves, the accuracy curves, with the lambda values from 0 until 0.1, with increasing some intervals. What you see here essentially is like there is really no clear trend. Like you can't really observe that as we increase regularization, things become better or worse. You're gonna see some randomness in these, and this is not because of regularization itself. This has to do with the data that we're playing with. If you run this code multiple times with different random initializations of the weights and whatnot, you're gonna end up also with different curves. So as I said, the data we're using is not very representative, but this is really up to you to go and find other data sets where you can very, very strongly see the effect of regularization. Okay? All right. This is just showing the effect of regularization on the last set of epochs. I think I'm plotting, from 500 to 950 epochs, just summarizing the accuracy from each regularization value and plotting this in the train and test data. You will see, for example, here that in the 0.05 regularization, looks like the model didn't really do well. Again, I would argue that this is a property of the data, and if you are to run this entire thing again, this curve is gonna look different. But again, this is up to you for testing. The L1 regularization is slightly different because there is no direct implementation of L1 in the PyTorch. So what we will have to do is we will have to take the mathematical equation that we just learned and apply this directly to the loss inside the model. So when we structure the model, what we will have to do is this is what we have to change. So the loss value, this term did not exist before. What we're doing here is we're calculating the loss one term, which is basically what we're doing is we're using the torch.sum, which is the sum of the absolute values of the weights, right? So we're getting the weights from where? From the parameters of the network, which we described before. Remember when we talked about the attributes of the network, probably in the first time we've done this, um, we said that we can use these attributes to access the weights and the biases, and that's what we're doing here. We're making sure that we're getting only the weights because that's what we use in regularization, not the biases. So if the bias is not in the name, meaning that take everything that is not a bias, take the absolute value. Sorry, I messed this up. Take the absolute value and then sum all of these and then add these to the final loss term or the L1 regularization term. Okay. And this is the actual application to the loss function, right? We're basically taking the loss and applying and adding the L1 term, multiplying first the L1 by lambda. This is the scaling factor. And then we're dividing by n weights. Can someone tell me why exactly am I dividing by n weights here? I just scrolled up so that you can see.
عشان أبقى أخلي فيه sparsity.
No, sparsity comes from the L1 application itself. The sparsity comes from the model as it learns.
أنا
Now we're
قصدي إن
changing.
أصفرهم يعني.
No, but we're not really using math to add sparsity. Sparsity comes from
by
as a
itself
result of the method. What's that?
by itself بقول.
Yeah, it comes as a result of adding the L1 term to the loss. It doesn't come
أنا
from
بحسب equation بحسب ليها mathematical equation.
no, the all the math is actually here, like exactly what we described here. I can go back to no, I went too far. Hold on. So this is basically all the this is all the this is all the math. There's nothing more to do. But then in my code, I'm dividing by the number of weights. Why am I dividing by the number of weights?
To take the average.
Average of what? So think about what I'm doing here inside the loop.
هو أنا أكني بوزع اللوس على الويتس كلها ولا أنا؟
Yes, so it's kind of we're basically we're going through. So this is actually the number of the total number of weights in the model. I'm actually doing this outside of the training loop, right? So I'm setting this initially to 0, and then I loop through the name parameters, and again this is the same code that I'm using. If bias is not in the name, I count these numbers, right? And then why do I need to do this here? Let's go back to um It's not here. Hold on. Yeah, the answer is here. Okay, how about you think about this and you tell me why am I dividing by the number of weights here? Okay, hopefully we get some answers in the Discord. Type. So the back to this, we're just gonna put this on the back burner for now and wait until you tell me why do you think this is the case. So back to this, the L1 term addition here, this is not something that PyTorch has built in, much like the weight decay, which we just add to the optimizer. So we have to implement this ourselves. The rest of the code is exactly the same. I'm plotting and showing you the loss, the difference between accuracy and the train and loss. And then I also am showing you the same idea of having some range of lambda values and how this basically affects the accuracy of the models. And again, you'll see that the different models here are basically very close to one another, that you can't really see much difference between them. One more time, it's not a property of the loss, it's a property of the data itself. And if you think about this data, the data has only 4 features. If we're making the weights sparse, we're really not not doing the data a good favor here. So typically, you will see the effects of regularization being L1 or deeper networks with more input features and whatnot. So then one thing I wanted to discuss, it's also one thing that I've wanted you to look into, is this. There's basically a third term of, oh, it's not really a third. There is a term, a regularization term, which combines both the L1 and the L2, and this is called the elastic net regression. Again, this is a board concept from statistics. The idea here is we don't really, in some cases, we don't really want to choose between one or the other of the regularizations, right? We talked about how L2 does well in terms of penalizing the really high weights and try to bring everything to zero, but it doesn't really set anything to zero. And how L1, on the other hand, forces because of its linear approach, because the reduction in weight is all actual face and achieve this um, cost to set zero, which caused the weights to be sparser. So this concept here of elastic net regression is with L2. And then you can add both terms to your cost and basically, depending on how you set the lambda, decide whether you want to have more contribution to L1 or whether you want to have more contribution to L2. And I wanted you to actually use the code here, the L1 code here, as an inspiration or a guide on how you would basically, by changing this code here, how would you implement the elastic net regression in your training? Should be very, very simple. This basically is what you need to do, but also have a term for the L2 and have a separate lambda for the L2. And instead of saying the loss equals loss plus the L1 term, you also would like to add or want to add the L2 term here. And obviously the L2 term here is, because you want to do this, the L2 term here is something that you want to calculate manually, because if you let PyTorch do it for you, then it becomes a little bit messy and you don't really see where things are happening in the background. So the cleaner way, as I would do it, is to manually calculate the L2 term. The math is hopefully straightforward that you can do it, and then you just set the loss to loss plus L1 plus L2 term. But this is left for you to play around with. Hopefully it's straightforward enough. So what are the advantages of ElasticNet? Just very quickly, because I would like to move on to the batch normalization. The main advantage of ElasticNet is it gets away from the idea of randomly picking one feature out of the collinear or correlated features in your space. Like we talked extensively about why the L1 regularization causes the basically the any set of correlated features to be all zeroed out at random and just one feature is kept in the final model. In the elastic net regularization, the behavior changes so that instead of dropping out a lot of these features, you actually keep most of these features, but because of the L2 term, you minimize their weights to a much smaller values. So you end up, instead of having, let's say, 10 co-regulated genes, instead of randomly having one of them being represented in the final model and the other 9 being dropped out, you get to keep the 10 genes while having smaller contributions from the weights of every one of those genes. And this is very useful in models where you would like to keep the features even if these features are co-regulated or even if these features are correlated to one another. So this is one of the main strengths of the ElasticNet model. There's others. You can Google why people like to use ElasticNet regression. In more cases than not, it's the appeal of trying to have some penalty on very large weights without wanting to drop out or having a lot of sparse weights. Another case, which I think I put somewhere, is if you were, maybe I put this in the L1. Yes, okay. I thought I put it somewhere. So in L1, what if I know beforehand that all the features in my data set are important? Like I have a data set, I know that all these features need to go into why the model, how the model makes a decision and how the model is trained, and I don't really want to drop out any of the features. So I can obviously use L2 just to start with, but maybe I would like a little bit more regularization. So I can use ElasticNet and not have as much sparse set of weights as would just L1 regularization give, as much as the L1 regularization would yield in terms of the model. So there are some situations where you could think about like which regularization is going to work best. And sometimes it's very clear that I really want to use L2 here or I really want to use L1 here. And there are some times where you're like, you know what, I'm just going to get the best of both and I will use the elastic net.
هو أنا مش فاهمة الفرق ما بينها وما بين ال L2 قوي، يعني حاساها هي شوية يعني.
Are you talking about the elastic net or? So the elastic net still has some L1 regularization.
بس احنا
So
مش
there's
حاجة زيرو بتهيألي.
no, you can. It's gonna be at much lower rate because you balance out between the L1 term and the L2 term. So you can end up having some sparse. You can end up having some sparse. You can end up having some weight set to zero. I don't want to call it sparse because the sparse term suggests that a lot of the weights are set to zero. So you're not going to have a sparse weights matrix, but you can have some weights set to zero. Some weights can just be noise and you're not really learning anything from it. So you benefit from setting these to zero.
اوكي.
The example that specifically doesn't set weights to zero is the example where you have correlated features, because like we explained, the idea of the correlated features is the model already knows that these features are important to the predictive power of the model. But if you only use the L1 term, the model, in order to minimize the cost function, it just wants to keep a single term of them because all of them provide the same information to the model, but all of them also add to the cost of the model. So it's in the model's best interest to only keep one of them to minimize the cost while maintaining the predictive power. When you apply elastic regression, the outcome of this, and again, this is very empirical result, the outcome of this is specifically in the co-express features or the correlated features, I want to say, you get to keep all of them. The model doesn't really drop all of them because now having smaller weights using the L2 regression minimizes this cost. But it doesn't mean that you're not going to have a single weight to not be zero.
اوكي فهمت.
So think about it as like just two extreme cases and you're trying to get to a middle ground. So when you have both terms together, the model is going to favor not having large weights because of the L2 term, and it's also going to favor having some weights to being zero because of the L1 term, but it's not going to push either of them to the extremes, basically. And then the result is hopefully the model learns sorry, hopefully the model learns the relevant features, and as it's training, it will keep the weights to a minimum. But so let me ask you a question here. How do you know, like we said, that you can control how much L1 and how much L2 using the lambda 1 and 2? How would you know how much of each one of them to use?
اعتقد على حسب الفيتشرز، يعني لو حاسه ان في فيتشرز كتيره ملهاش لازمه فكده هستخدم L1 اكتر.
Taib, if you don't really know much about your data, so again, the same example I just mentioned, like you did a sequencing experiment and you have 15,000 features. Obviously, you don't really know much about the 15,000 features. So you'd like the model to learn which features are important, for example. And you're trying to use elastic net because it looks like this is the way to go, but you don't really know which values of lambda 1 and lambda 2 to set.
اعتقد هبص للويتس.
The
هبص
15,000 of them?
لا برضو هيبقى 15,000. لا اعتقد ممكن اعمل 0.5 لان مش عايزه اهبط الصراحه.
Go back 2 lectures. Think about what we discussed before the regularization. What's
خلاص.
your read? How do you know if your model is doing well or bad? You do cross-validation, right?
Right.
You do cross-validation. So in doing cross-validation, now you have your training data, your evaluation data, and your testing data. In the evaluation mode, this is basically where you would go through. So you would train different models using different ratios of lambda 1 and lambda 2. And then using your evaluation data set, you would see how the model performs on the evaluation data when you have different ratios of lambda 1 and lambda 2. And if you're using too much L1 that you are throwing out way too many features, this is going to degrade the performance of the model. If you're using way too much L2 and shrinking the weights too much, that the model is not really learning the features or not, and you're taking away the expressive features of the model that it's not really it's not able to represent a lot of the features properly because all the weights are really getting shrunk towards zero, then you will know that you're using way too much L2. So the same way, like I'm putting these experiments, the parametric experiments here, not for fun.
بعمل validation بغير ال probability بتاعت كل واحد.
Yeah, so you basically do what we call a parameter sweep. So you're sweeping through the parameters, you're setting different combinations of L1 and L2, and then this is the purpose of the entire cross-validation like we described it. You have your training data, which is maybe 80% of your data, you have your evaluation, you have your test. As you're selecting your parameters and your cost function and whatnot, you're basically using the evaluation data set. And once you have the best performance in the evaluation data set, you go and test on the test data set. But like as we said in the beginning, you can theorize as much as possible about like which one to go and how much do I know about my data. But eventually, what will make a decision for you is once you apply these parameters or a sensible range of these parameters on your model and you look at the output of how every model behaves, this is going to be the best model that you will pick. Even with the same features, I think I mentioned this before, you typically never train a model once. For me, in my practice, I usually, let's say, train three models using the exact same parameters. But because of the randomness of how the weights are initialized, the randomness of how many batches are sampled, because of the randomness of how train and test data sets are split, you're going to see differences. And eventually, the model you choose to publish or productionize or to save the weights of is the model that performs the best. Why is it the best given that three models have exactly the same parameters? Because of the randomness of how things are done. But if you're doing the parameter sweep, like you're trying to identify what is the good balance of L2 versus L1 regularization in my model, this is a very strong use case for cross-validation. Okay.
Okay.
All right. So the last thing I would really like to discuss here, I didn't even put the code for it because I knew we didn't have time. But so going back to, the beginning of last lecture where we said the regularization could be generally classified into node level regularization, which was the dropout, and then loss level regularization, which is everything we talked about in the last hour. L1 and L2 and stuff. And you can kind of see that we are applying regularization directly to the loss term inside the training. So the loss is the term that is being regularized here. I am adding a term to penalize certain weight values at the stage of calculating the loss. And then the last mode or type of normalization, if you will. Again, this is not really a formal classification. This is just something to mentally think about these different types of regularization in a structured way. So the last thing is on the data level itself. So data normalization by and large. So the data normalization has basically two ways of doing. The first and most straightforward is you input you normalize your input features. And this is something we described before. And this is something that is not specific to deep learning. Again, either going back to classic machine learning examples like predicting the price of a house from a set of features. If you have some of these features as, the number of bedrooms or the square footage or stuff like this, you're going to see that these features are in a massively different scales, right? So if number of bedrooms is going to be like 1, 2, 3, 4, let's say, and then I don't know, square footage is going to be in like maybe 2000 square feet or whatever. So the scale of the features themselves are really going to be very different. And when you go and then take every one of these features and multiply it by the same weight, the response or the output is going to be very different. When you multiply 2 by a weight of 2 is going to give you 4. But if you multiply the input of 2000 by 2 is going to give you 4000. And again, we go back to the same principle of the other, like when we described at the beginning of this lecture, when a certain weight is too big or too large, this makes the model too sensitive to a small change in the input. And this is again the same idea, but on the level of the data. You would like the features to be on the same scale so that when you go and multiply them by your weights, you don't really bias the model to one way or the other just because of the absolute value of this, the absolute value of the feature itself. Because to the model, the absolute value of the feature doesn't really make any difference. Like the model doesn't care if you represent something as 2000 or 2, as long as the differences between these features is the same. So in order to do this, we use the normalization procedure. And the normalization, as I said, is something that is, we can think about it in two different scenarios. The first is what we apply to the input data ourselves, just what I described. And then the the normalization that gets applied to the values as they propagate between the layers. Remember, if you think about the layers, I gave this example before, and I'm going to say it again. Every node inside the network doesn't really know the structure of the network around it. Like the node just gets some number. The number is referred to as input. This input could be the raw data input, if this is the input layer, or it could be the output of a previous hidden layer, if this is in the hidden layer, or if it's the output, it's like if this is the output layer, its input will be the output that comes from the last hidden layer in the model, right? So there is, just generally speaking, some form of input coming to every node. Whether this input is our raw data or this input is the output of a previous layer, it is some form of number that goes into this node. And the reason why we make a distinction between the input normalization and the batch normalization is that the batch normalization cannot be treated the same way as the input normalization. And this is a discussion we're going to have next time. But for now, what I would like you to see here is that there's very two simple forms of normalization that we usually apply to the data. One is the z-scoring. I am hoping that most of you have heard of this before, which basically means that we mean center all the data points around 0, and we set the standard deviation to 1. And in order to do this, all we have to do is we take every one of these values, we subtract the mean of this of the data, and we divide this by the standard deviation. This is very popular and it has tons of applications, the z-scoring. It's also called standardization. So standardization is like a special case of normalization. When you subtract the mean and divide by the standard deviation, it's called standardization. Is also called z-scoring. The other kind of normalization that we can apply is called min-max scaling. And what you basically do here, in very simple terms, is you look at the data, you take the maximum value of the data and you set this to 1. You look at the data, you take the minimum value of the data and you set this to 0. And then you shrink all the values in between, obviously proportionally. One of the disadvantages or drawbacks of min-max scaling is if your data has lots of, maybe not lots, maybe a couple of outliers. Like let's say you have an input feature that all the values are between 0 and 10, and then you have a single value that is 100. If you apply min-max scaling in that case, your basically 100 becomes the 1, and all the other features that are between 0 and 10 are going to be between 0 and 0.1, basically. So you're really just not well representing the features in that case, and you're going to run into the same problem that you ran into when it comes to the scaling of the inputs by the weights, because one is going to be very high and the others are going to be very small. So this is something to be aware of, and the choice of whether you do z-scoring or min-max scaling comes to the nature of your data. So one thing you would kind of consider doing before deciding which one to use for normalization is you would just plot your data, look at the distribution of the data, and then decide which way do I want to go? How do I want to normalize my data? I want to say by and large, z-scoring is much more commonly used because of its property in centering the data around 0 and expressing the changes as scales of the standard deviation, essentially. But there are cases where you want to use some min-max scaling depending on the range of your data. The batch normalization is something that is done with the same spirit, but we add a little bit of spin to it. So the way it works, I'm just going to mention this quickly, and next time we can discuss it in more details. It uses exactly the same principle of the input feature normalization. So you compute the mean, the standard deviation, and then you do a z-scoring. There's just a very slight change to z-scoring here. We are adding a small constant, which is epsilon here. And this is just to get away from, if you end up having a standard deviation of 0, you would basically want to get away from dividing by 0. So this is not really changing anything about the standardization. We're just trying to catch any edge case where the standard deviation is 0. Then this is going to break the math within the network. So you just add a small term so that this doesn't break mathematically. The real change here, and when it comes to batch normalization, is that you don't really take the z-scored x values and pass them to the activation function. Like, remember now, this is happening inside the hidden layers, right? So this x here is basically gonna be the x value that you pass it to, that gets multiplied by the weights, and then it gets passed to the activation function. So before we take the z scored or the z normalized x values, we actually do a single step to scale and shift these values. And how we do this is we use a parameter called the gamma to multiply the x by it. So this is the scaling term, and then we also add a beta, which shifts this a little bit. I would like you to think about, why do we want to do this, rather than just doing the z scoring, and what advantage would this give us? And just to give you some hints, think about the activation functions and how these activation functions behave around the zero. Remember that the z scoring is a procedure that sets the mean to zero. So a lot of the data, a lot of the distribution of the data will center around the zero. And only the kind of, as you get away from the zero, the less data points you will have. So think about why we want to apply some scaling and shifting of the data after we do the z scoring. We're going to talk about it next time in more details, but maybe something to think about. Any questions?
حضرتك من شوية قلت لي يعني أقدر أعرف مثلا نسبة ال L1 وال L2 من خلال ال validation، يعني بعد ما أعمل ال validation أو كده فأنا أشوف هل هحتاج أغير فيهم ولا لأ.
Yeah.
فأنا كنت عايزة أعرف يعني هعرف منين المشكلة في ال L1 ولا ال L2 ولا ال learning rate ولا number of hidden layers، يعني قصدي في حاجات كتيرة يعني هتيجي في بالي لما ألاقي ال validation قليلة.
حلو. سؤال جميل جدا. This has nothing to do with deep learning. What do you study?
Computer and data science.
طيب، كان نفسي تقولي لي biology. scientifically speaking، بره ال deep learning، تمام؟ let's say أنا عربيتي باظت، حلو؟ عندي مشكلة، ممكن يبقى اللي بايظ في العربية ممكن يبقى جاي من الموتور، أو جاي من الترانسميشن، أو جاي من العجل، صح؟ This is exactly your question. How would I know where the problem is coming from?
أيوة أنا بسأل.
طيب the solution is، حد ممكن يجاوب؟ حد عنده أفكار؟ يعني what do we do in this? Because this is a very common thing we solve in science all the time. It doesn't matter what discipline you are. You have sources of variation coming from, or you have some form of a variation or an output that comes from multiple sources, and you would like to know which source is responsible for what I am observing.
هشوف اي سورس من دول وهغيره واشوف لو ده هيأثر على الفاريشن اللي طالع لي.
تمام. You fix everything except for one variation. Then you vary this up and down, and then you observe the effect. And then you repeat this with the other variations. So the idea is you're isolating one variable at a time. You cannot really scientifically do an experiment where you change both things at the same time. So you fix one thing and you change one other thing, and then you run your experiment and you observe the output. Then you go back and you fix what you just changed, and you change the other variable up and down, and you observe what happens. This is kind of the same mindset and the same philosophy that you can apply to any kind of problem where you have variation coming from. I mean, obviously, after having conceptually thought about the problem and maybe thought about where the things are coming from and yada yada. So eventually, this is what you do to find the definitive answer. So in a context of biology, for example, you would just take the same cell if you're suspecting that one of three genes might be having the effect. So you take the same cell, you knock out gene 1, you knock out gene 2, you knock out gene 3 independently in 3 different experiments, and you record the output. This way you know whether the effect is coming from gene 1, 2, or 3. Or maybe it's additive. So when you knock out the 3 together, there's a synergistic effect. So the effect of the 3 is more than the addition of 1, 2, and 3.
ما هي الفكرة ان هو الاحتمالات كتيرة قوي، فانا عشان كده كنت بسأل لو في طريقة يعني
No
اسهل.
one said it's easy.
هو
This is why you spend months optimizing a model, because this is only one thing. We're only thinking about, like, you are only thinking about regularization. You haven't thought about learning rate. You haven't thought about the actual architecture of the model. What happens if I increase the number of nodes per hidden layer, or if I increase the number of hidden layers altogether? What happens if I change my activation function? There's way too many things that you can possibly test given unlimited resources and time. This is why there is really nothing called or nothing as like the perfect model or the best model. There's always going to be the good enough model. And as long as something is good enough, you just use it.
مم.
Any more questions? It's not always cheap, by the way. uh, yeah. So if your models need to run on B200 GPUs and you need to train for a week or 2 weeks, uh, it becomes expensive, even just to run experiments on the computer. So yeah. And obviously in something like biology where you have to do experiments in cells and mice and stuff. Yeah. I'm not factoring in the cost of the person doing this and their time and their effort, but even just thinking about resources, it can become very expensive. That's why actually, um, that's why something like AI is making its waves in biology, because one of the very important things people are trying to achieve is to limit the number of experiments and screens they do by using the predictive power of models. So if a model is predicting that in that space, for example, if I'm looking to do a screen in order to identify some hits associated with a certain disease, instead of doing this when I am completely blind to the biology, if I train the model with the features, clinical features, and some genetic data and some transcriptomics data and what have you, if I throw these all into a model and then ask the model to predict what genes or what hits are gonna result in a new phenotype, or are gonna result in, I don't know, a certain progression in a disease or what have you, depending on your question, then this narrows down my search space a lot. And I can use then the experiments and the biology and resources to validate this rather than to screen this. So yeah, it can get expensive, and it's definitely not easy because of the number of the moving parts. And one thing to always keep in mind that we discussed many times, all models are wrong, some are useful. So you're not trying to be right, you're trying to be useful. Yeah. No, it's cheaper still than biology, I would say. Yeah. All right. So yeah, sorry for going over. We're already 10 minutes over. So um hopefully my ranting of 15 minutes at the beginning of the class made you a little bit motivated to go and look at the code and try things for yourself. Um, I would really like to see some people do things and ask questions, and um, hopefully the code in place is easy for you to follow and modify things and try things out and then come back with questions. If you fancy doing something more complicated, you can go in Kaggle, download some data sets. All you need really to do is plug and play the data. You will just, instead of me using the iris data, you will just download a different data set. You look at it, and then you try and apply some of the principles that we did as like let's say it's a classification data set or regression data set. The code should be very easy for you to modify and run your own models just to explore how things work. Um, Hopefully, um, people take this seriously. All right. I'll see you next time, inshallah. Assalamu alaikum.
عليكم
عليكم
السلام، مع السلامة.